Hello.
Hi.
Hi. Hello. We have Saikat with us today. So, Saikat, if you can introduce yourself. So, yeah, just before you introduce, Saikat is an experienced researcher and has been working in the US and Japan for some time. But I'll let him speak and maybe give an introduction of himself.
Thanks, Olive. Hi, I'm Saikat Basu. Right now, I'm a postdoc scholar at OIST in Japan. This is a very new institute. And I finished my PhD at Virginia Tech, majoring in engineering mechanics. Essentially, I worked in the area of fluid mechanics over there. And let me go back a little bit. So, for my undergrad, I did my bachelor's in civil engineering from Jadavpur University in India. And when I was finishing up my bachelor's, I had a couple of options, but I thought about going for a PhD. And based on my interest, I wanted to do something in fluid mechanics. And hence I applied to a number of graduate schools in the US. And eventually I went into Virginia Tech, where the problem I was working on matched with my interest in theoretical fluid mechanics. So from there, I finished my PhD in 2014, last year in May. And for the last 1.5 years, I have been here in Japan working again on fluid mechanics with some theoretical components, some experimental components, and some computational components as well.
Okay, that sounds great. A lot of experience. Uh, how has been like working? So you have worked in the U.S., working in Japan, and even I mean, I'm sure that you must have done some amount of research-oriented work in India itself. So
Yeah.
how was the experience overall? Like, were there any differences working in different places, or I mean, apart from the basic cultural differences? Well, I mean, is there anything like you want to share with us?
So tracking back since 2007, I have done some form of research in 4 countries. So I did some work in India. So I was selected as a summer research fellow for Institute of Mathematical Sciences in Chennai. So I worked there over the summer of 2007 as well as the winter of 2007. And the next year for summer, I worked at DLR in Germany for summer. And 2009 onwards, I was in the US. If you ask me to compare between India and Germany and USA and now in Japan, I would definitely rate USA as number one in terms of the research experience or the academic experience that students or researchers they are exposed to in that country. Speaking of India, I don't have much experience about the higher academic research, although I did some research over there and I was very satisfied with what I saw. And my first interest in research was instigated in India at IMSC. But IMSC is a very small institute and that is not a very good representation of the overall academic culture in India, the overall research culture in India. So I'm not the best person to opine about the Indian academic culture, but between Japan and the USA, I would definitely prefer USA more because in Japan there are lots of issues like if you are trying, for example, if you are trying to buy a certain equipment, the steps towards buying that equipment, the different clearances that you need to get, they are much more constrained in Japan than in the US. So in the US, everything is much easier. And also the big issue that I've been personally facing, and that's true for any foreign researcher here in Japan, is the language barrier. So although the institute where I work at, most of the researchers are from Europe or from US or sometimes from India, but the administrative stuff they are from Japan, and so there is a lack of communication between the Japanese people and people from elsewhere.
Mm-hmm.
So overall, yes, I have worked in a number of countries, but I definitely rate USA more because it's a multicultural society. There are professors from different countries, there are students from different countries. You get to know about different kinds of academic cultures, and eventually you find your own niche.
Makes sense. Yeah. So tell us more about what you worked on your like current research and your doctoral research. So what's I mean the broad area and like what was your topic about and what problem were you trying to solve basically?
Yeah. So before I go into the particular problems, let me just outline how I got inspired to work in these problems. During my high school years, mathematics was my favorite subject, and I wanted to do something in mathematics. But as we ended our high school, we thought about, okay, engineering is the most secure way to go about, so let's take up engineering. And based on whatever ranks I got in the engineering entrance exams, I had a couple of options like civil engineering or chemical engineering at Jadavpur University. And as a kid, I have always been inspired by certain other things like aerospace engineering, rocket science, space shuttles, the documentaries that they used to show on the history channels, on the Discovery channels, etc. And I always wanted to work on aerospace engineering as well, apart from mathematics. And I took up civil engineering because I learned that from civil engineering you can specialize in aerospace later on. I took up civil because at Jadavpur University they did not have the aerospace engineering department, which is a misfortune.
Mm-hmm.
So anyways, I started on civil engineering and gradually I found that I have some kind of knack for fluid mechanics. So I decided to go into fluid mechanics. And I went into Virginia Tech in 2009 fall. So for my PhD I worked in a theoretical fluid mechanics problem. It's on vortex dynamics. So whenever you place an object in a flow, for laminar flows, you see there's some well-distinct vortices formed in the downstream of the structure. And these vortex structures are shaped periodically into the flow. Now, as they're shaped periodically, typically in each period there are just two vortices. And over the last 100 years, all the engineering structures, they have been designed for these two vortex structure vectors. And these vortex vectors, they exert some force on the structure, so we need to account for that force to design a proper, safe engineering structure. But if we look at nature, there can be different other kinds of vectors as well. There can be vectors where in each period there can be 3 vortices, there can be 4 vortices, there can even be 5 vortices. But those are difficult to handle, and until now engineers, they have not used those kinds of vectors or the forces that those kinds of vectors might exert on the structure in their design calculations.
Mm-hmm.
So that was the motivation from where I started my PhD work, to develop some robust analytical models for those kinds of complex vectors. For my PhD, as part of my dissertation, I developed physical models for vectors with 3 vortices and with 4 vortices per shedding cycle. And I characterized the dynamics of those kinds of vectors, and I tried to find out what are the forces or what are the effects that those vectors can have on the body.
Right.
So that's overall my PhD work. And after that, I finished up in 2014 May, and I came to Japan. So over here, I'm working on another fun problem. So here I'm looking at what happens when a tiny droplet, if it hits a soap film. Now it hits a soap film at a very shallow angle. So the soap film is flowing vertically down under pressure head through an inclined network, and the vertical drop hits it vertically, so it just falls vertically and hits it at a very shallow angle. Now think about the situation. There is a film, there is a drop hitting the film. What can happen? There can be 3 kinds of impacts. It can either pass through the film, it can break through the film, or it can get stuck on the film surface and move molest with the film surface and move downstream. And there can be a certain situation where the drop bounces off the film surface. Now we saw that when the angle of impact is less than 10 degrees typically, the drop always bounces off the film surface. So my problem here is to figure out the different parameters for which this bounce off regime will happen always. So what parameters? The drop size, the film velocity, the surface tensions, the angle of inclination, the angle of attack of the impact, etc. So I'm trying to figure out the bounce off regime and what are the parameters that would lead to this kind of regime. And as for applications of this particular problem, yes, so here we essentially have a splash of liquid entering into another big jet of liquid. So those are relevant for certain biomedical applications as well, where we're trying to inject something into a flow through a vein, and how that drug would interact with the vein flow and how everything would mix up after the impact. And so this is the application for my postdoc problem. For the PhD problem, I know, yes, as I said, that I was inspired by working in theoretical fluid mechanics, and hence I decided to work on that problem. But as I was finishing up my PhD work, my work on vortex dynamics during my PhD, we figured out that there is a very fun way to look at things and how this can be applicable to real life. So as I said, when vortex vectors, they are formed behind a structure, they exert some forces on the structure as well. Now think about this, like if the structure is free to move, the vortex vex can make the structure move freely. So if the vortex vex can make the structure move freely, there is some form of energy is available from those vortex vex. So in this age, when we are in shortage of energy everywhere, this can be a very efficient way of at least extracting some small amounts of energy. So I developed a certain device which can use that vortex motion to harness some renewable energy and use it for, so once we have that mechanical energy, we can use a gear assembly to transfer it into a generator and we can extract that energy as usable electrical energy. So that's one possible application that is there from my PhD. So
Okay.
these are the two major problems that I have worked on until now.
All right. Yeah. So great, a great, lot of experience. It speaks for itself. Uh, Actually, it was interesting. You explaining about vortices and tell me more about like. So there are a lot of mathematics involved. Like in fluid mechanics, typically you have a lot of mathematics. So and also obviously physics is there. So like when you're trying to build the analytical model. So I mean, so what kind of mathematics did you use, and how challenging was it? So like, what kind of tools did you use? Like, what kind of calculus did you use, or what was it about actually?
Okay, thank you. This is a good question. Let me first come to the challenging part of it. So the biggest drawback that I found in the Indian education, I think a high school student, an Indian high school student, after he or she has finished the 12th grade, he or she is a much better student than an American student. But during the 4 years of our academic studies, during our undergrads, we hardly improve ourselves in terms of our knowledge or in terms of how we apply our knowledge. Yes, we learn a few new techniques, we imbibe few new skills, but we don't really invest ourselves entirely into learning a whole different skill set. Or even, so I'm talking about this because as Olive just asked me that what kinds of mathematics I had to use for my PhD work. Typically the things that I use that should have been taught in our undergrads, they are there in our undergrad syllabuses. So if I look at the premier institutes in India, those things are there. But somehow in our engineering curriculum education, we ignore on the mathematics education. We just focus more on the third year and fourth year subjects, and we just figure, okay, if I am a mechanical engineer, I have to learn these particular courses, and then we are good to go for the industry. Similarly for civil engineering, but it's important to know physics, it's important to know mathematics. So when I first went to the US, my first semester was quite grueling because I had to bridge up that knowledge gap. Some of the things that I should have learned beforehand, I had to again refurbish my knowledge and make myself acquainted with those things. Anyway, so for my PhD problem, I used a particular dynamical systems tool. It is called Hamiltonian dynamics. Now, let me say a few more things. So we know that any fluid mechanics problem is governed by a set of partial differential equations called Navier-Stokes equations.
Right.
So we can just use Navier-Stokes equation to solve fluid mechanics problems, as anybody would probably presume. But no, for example, in the problem that I was working on, it's an infinite degree problem where you have to know the exact dynamics of the vortex vex. If you have to use Navier-Stokes equation, you have to use the Navier-Stokes equation for each and every fluid particle, which is not possible physically. So you have to make the problem, you have to reduce the order of that problem. You have to make the problem much simplified. So what did I do? I looked at the experimental vex. So we looked at the experimental vex, which has like 3 vortices or 4 vortices. And we looked at how the individual vortices are arranged with respect to each other. So by just looking at the experimental vex, you can make some assumptions regarding the geometry of the problem. That okay, the individual vortices within a period, they will be arranged with respect to each other in this kind of geometry. So once we place that geometrical constant on our system, it becomes a reduced order problem. It becomes a reduced order problem. We can assume a few other things as well, like we can assume certain things about the impulse of that periodic setup, the streamwise impulse as well as the transverse impulse. And after all these assumptions and after those geometrical constants being imposed on the system, it is possible to reduce that infinite order problem into a finite order Hamiltonian system, where Hamiltonian is a quantity which is staying preserved in our system. It's a function of the locations of each of the individual vortices as well as the vortex circulations. So once a problem can be expressed in terms of a Hamiltonian, from the Hamiltonian we would have some equations of motion for the problem which are called the canonical equations of motion. So once we have the equations of motion for the problem, we can just just integrate those equations of motion to numerical integration and find out the different trajectories that are happening for certain different sets of initial conditions. So that was the overall idea with which I attacked my PhD problem. And as for the problem that I'm working on right now, it's a very simple problem because as I said, when I'm just looking at the regime when the drop impacts and bounces off the film surface. Essentially, it's a 7th grade problem. So what is necessary for the drop to bounce off the film surface? Think about this. The film is flowing, the drop is bouncing off the film. Now, before it bounces off the film, it impinges into the film surface, and as it impinges into the film surface, there is a very minute instant where it stays static. So just think about the static analysis. The drop has deformed into the film. Think about all the forces that are acting on the drop. And if the forces are strong enough to push the drop away from the film surface, then it will bounce off the film surface. So my work is just to track the different forces that are acting on the drop and see if they're strong enough to push it away from the surface. And if they're strong enough, that's the particular phase region, that's the particular parameter region where the bounce off would happen.
Right.
So it's just force analysis for this current problem that I'm working on.
Okay. And so for example, so the vortices, so the Hamiltonian things which you Hamiltonian equation, canonical equations which you have used. So did you need to solve those equations to come up with some solutions? So for example, did you use any data or did you do numerical analysis? Supporting by some data. So how did you go about it? Like or what were the final solutions like? Were there some kind of a series of some kind of series, typical series which you get in mathematics, or was it some kind of a condensed analytical form? So how did you come up with the final solution? So any tools which you have used, which you can talk about?
Okay. So let me think about just one particular vortex setup. Let me think about the setup where in each period we have 4 vortices. So with 4 vortices in a periodic setup, the Hamiltonian is well known from literature. Like this is the Hamiltonian that should be there for a 4 vortex system. Now for our particular Vex system, we had to, so that particular Hamiltonian is a function of locations of all those 4 vortices. But so that means that Hamiltonian is dependent on all those four parameters. But to visualize a problem, so the target was to plot the Hamiltonian contours on a 2D plane.
Okay.
To plot the contours on a 2D plane, we need to reduce that 4-order problem to a 2-order problem. So what did we do? We assumed that by looking at the experimental Vex, we assumed that we assumed that there are 2 main vortices and the other 2 vortices are mirror images of those vortices separated by some transverse, some streamers distance. It's difficult to explain that in audio, but we assume certain geometrical constant on the locations of the vortices.
Okay.
So that the entire geometrical setup can be expressed as the relative separation between the 2 main vortices. So let me call it as delta x and delta y, the separation between the 2 main vortices, the x separation and the vertical y separation. And after a great deal of algebraic manipulation, it was possible to reduce the first Hamiltonian to a Hamiltonian where it's a function of this delta x and delta y and the 2 impulse components, the vertical impulse component and the linear impulse component, and the horizontal impulse component. And while plotting the Hamiltonian, we assume certain values for these impulse components, but the delta x and delta y, which are the relative separation between the main vortices, those could be valid. So think about this. So there is a contour. Some of the contours that look like a dumbbell. So a particular vortex setup would always occur along that dumbbell, but the Hamiltonian is a constant of motion, right? So the Hamiltonian value would stay preserved. So to ensure that the Hamiltonian stays preserved, the delta x and delta y should be varied in such a way that they always stay on that dumbbell-shaped contour. So by the variation of that delta x and delta y, the relative positions of the vortices, they are also varying because delta x and delta y, they are changing. And they are changing in such a way that the contour is always preserved. So that was the main idea. And as for if we did any numerical integration, how did we compare them with real vex? Yes, we had a collaborator group in Denmark, in DTU, led by Thomas Bohr. He is one of the most noted field mechanicians currently. So they did a number of experiments on soap films. So what they did, they had tiny airfoils and they flapped the airfoils on a vertically filmed soap film, and they generated a number of different kinds of vex. We compared our data with the 4 vortex vex from their experiments with our model. We knew the initial parameters like what are the impulse values, what is the initial delta x and delta y when the vortices start to evolve, and we plugged that into our model and we did a numerical integration over a certain interval of time, and we tracked the model trajectories with the trajectories that we see from the experiments, and the fit in the model and the experiments were very satisfactory. We already have 2 papers on this model as well as the comparison. One is in physics of fluids, the other one is in fluid dynamics research. Right now I'm working on another manuscript which goes more into the experimental comparison and whether how fit our model is in predicting the evolution of vortex vex.
Awesome. Actually, very, very interesting. I think this detailed explanation, I think, which you have given sort of is very inspiring. I think probably for a wider audience. And that now that I mean, especially coming from an Indian perspective, this kind of in-depth understanding of fluid mechanics and how people in research are thinking about it, what kind of tools they're using. I'm sure this kind of information is like quite valuable to people, and most often, I mean, we keep on hearing stuff from not from you people who are actually doing the research, but more from the journals and newspapers and a lot of other media where probably one information which moves ultimately it gets truncated in a way. So it's great to hear directly from you, and I'm sure this will be really inspiring for people. So I
think one thing I would want to add, certain changes can be done to our undergraduate education. As I said, our high school students are possibly the best in the world, but once we finish our undergrads, we are not the best possible engineers in the world, both as researchers as well as practicing engineers. So I think we should think about what changes we can make to our undergraduate education, whether we should include research component as part of they would do some research and it get some grades and which can even for certain grades later on in a much more constructive way, not like the way that we have right now where people are not that serious about research at the undergraduate level. So I think there is a scope to think about the standard as well as the contents of our undergraduate education in India.
Makes sense. Valuable advices which you've added. So I'm sure this will be very informative, and I'm sure if it reaches to a larger audience, I think they can definitely think about it. So I'll probably keep it short here. So, but I'm sure this is not the final time which we are talking. So probably we'll disturb you again and try to know what you are working on. When your next endeavors, and probably again. Or maybe get into further details of particular topics. So, but that's for the next session, not now. So, very nice talking to you. And
thank you, Ali. It was nice talking to you as well.
Yeah, sure. And I'll probably talk to you later then. Yeah, bye.
Thank you. Bye.